In October 2018, the world watched in horror as Lion Air Flight 610 plunged into the Java Sea, claiming 189 lives. A mere 5 months later, Ethiopian Airlines Flight 302 met a similar catastrophic fate, killing all 157 on board. These were not isolated incidents, they represented a profound crisis for Boeing, a company long synonymous with aerospace excellence and safety. For decades, the mantra "if it's not a Boeing, I'm not going" epitomized trust. Yet, two brand new aircraft, the Boeing 737 MAX, had crashed within months. This alarming pattern indicated something far more troubling than simple misfortune. It pointed to deep-seated systemic failures. The immediate aftermath brought a barrage of questions. Was it pilot error? A manufacturing defect? Or something more insidious woven into the very fabric of the aircraft's design and the company's operational philosophy? Our analysis aims to cut through the noise, revealing that the real reason for these crashes isn't singular but a confluence of interdependent factors. It's a story of ambitious engineering compromises, regulatory missteps, and a corporate culture that, many argue, had strayed from its safety-first roots. We will dissect each layer, from the aircraft's crucial software to the oversight process, to understand how a titan of industry stumbled so catastrophically. For nearly a century, Boeing embodied American engineering prowess. From the iconic B-17 Flying Fortress to the revolutionary 747 jumbo jet, their aircraft were testaments to innovation and unwavering reliability. The company's ethos was once defined by its engineers, individuals who prioritized safety and technical excellence above all else. This culture fostered groundbreaking designs and a stellar safety record, earning the trust of airlines and passengers worldwide. It was a time when complex machines were built with meticulous care, and design integrity was sacrosanct, creating a legacy many believed was unshakable. A pivotal moment arrived in 1997. Boeing merged with McDonnell Douglas. This acquisition marked a significant cultural shift. McDonnell Douglas, known for its cost-cutting focus and emphasis on shareholder value, arguably diluted Boeing's engineering-centric philosophy. Many former Boeing employees and industry observers point to this merger as the turning point, where financial metrics began to overshadow engineering excellence. The focus shifted from "what can we build" to "how cheaply and quickly can we build it," setting a precedent that would resonate deeply within the company for decades, ultimately impacting critical decision-making processes. By the early 2010s, Boeing faced intense competition from its European rival, Airbus. Airbus's A320neo, with its new, fuel-efficient engines, was selling exceptionally well. Airlines were clamoring for next-generation narrow-body jets that promised significant operational cost savings. Boeing, under immense pressure to respond quickly and not cede market share, decided against designing an entirely new aircraft from scratch. A completely new design would have taken years and billions of dollars, a risk management was unwilling to take given the competitive landscape. This strategic choice, driven by market urgency, laid the groundwork for the 737 MAX problematic genesis. Instead of a clean-sheet design, Boeing opted to heavily modify its best-selling 737, an airframe that dated back to the 1960s. The MAX designation represented the fourth generation of the venerable 737. The primary change involved fitting larger, more fuel-efficient CFM LEAP-1B engines. This approach offered a quicker path to market and significant cost savings by leveraging existing designs, training programs, and tooling. Airlines loved the idea of maintaining fleet commonality. However, adapting a 50-year-old design to accommodate modern engines proved to be an engineering challenge with unforeseen consequences, particularly concerning aerodynamics. The new, larger CFM LEAP-1B engines had a higher bypass ratio, meaning they were physically bigger. To maintain sufficient ground clearance on the 737's relatively low fuselage, Boeing had to mount these engines further forward and slightly higher on the wings. This seemingly minor change significantly altered the aircraft's aerodynamic characteristics. During certain flight maneuvers, particularly at high angles of attack, the forward-mounted engines created an aerodynamic pitch-up moment, raising the nose excessively. This unexpected behavior necessitated a software solution to ensure the aircraft handled similarly to previous 737 generations, a key selling point to airlines. To counteract the pitch-up tendency caused by the new engine placement, Boeing developed the Maneuvering Characteristics Augmentation System, or MCAS. This software was designed to automatically push the aircraft's nose down if it detected a high angle of attack, AOA, during specific flight conditions, thereby preventing an aerodynamic stall that pilots might not anticipate. In theory, MCAS would make the MAX feel like any other 737, avoiding the need for extensive pilot retraining, a major cost-saving and selling point for airlines. However, the system's criticality and its operational details were largely kept from pilots and even some regulators. A crucial and controversial aspect of MCAS was its limited disclosure. Boeing categorized it as a relatively minor system, intended to operate in the background and only activate in extreme, high-speed flight regimes. Consequently, it received minimal attention in pilot manuals and training materials. Pilots transitioning to the 737 MAX often received only a brief iPad-based training module, not full simulator training, because the MAX was certified as a variant of the 737, not a new aircraft type. This lack of transparency meant pilots were largely unprepared for the aggressive and unexpected behavior MCAS could exhibit, particularly in abnormal conditions. On October 29, 2018, Lion Air Flight 610, a brand new 737 MAX 8, departed Jakarta. Shortly after takeoff, the aircraft began to experience erratic flight control issues. The pilots struggled to maintain control as an automated system repeatedly pushed the nose down, despite their efforts to pull up. After a desperate 13-minute struggle, the plane plunged into the Java Sea, killing all 189 passengers and crew. The crash shocked the world, marking the beginning of the end of Boeing's perception of invincibility. It was the first chilling sign that something fundamentally flawed was lurking within the 737 MAX sophisticated systems, far beyond typical operational glitches. The recovery of the aircraft's flight data recorder, FDR, and cockpit voice recorder, CVR, from the Java Sea was crucial. Analysis of the black box data quickly revealed a horrifying pattern. The MCAS system was repeatedly activating, pushing the aircraft's nose down, based on faulty data from a single angle of attack, AOA, sensor. The pilots were fighting an unseen adversary, struggling against an automated system they didn't fully understand. The data showed the captain and first officer engaged in a frantic battle for control, trying to counter the erroneous commands, a struggle that ultimately proved insurmountable given the system's aggressive nature. Central to the MCAS malfunction was the angle of attack, AOA, sensor. This small vane-like device, mounted on the side of the aircraft's fuselage, measures the angle between the wing and the oncoming air. Accurate AOA data is vital for flight control, especially in preventing stalls. On the 737 MAX, there are two AOA sensors, one on each side. However, a critical design choice in MCAS was that it relied on input from only one of these sensors. If that single sensor failed or provided erroneous data, MCAS would activate based on incorrect information, without any crosscheck, triggering its nose-down commands. The design of MCAS permitted it to activate repeatedly and aggressively based solely on a single, erroneous angle of attack sensor. There was no mechanism to compare the input from both AOA sensors, or to provide an immediate warning to pilots about a discrepancy. Furthermore, MCAS, once triggered, commanded a significant nose-down trim adjustment up to 2.5 degrees and could reactivate every 5 seconds, even if pilots were simultaneously trying to correct the aircraft's pitch. This aggressive, unmitigated behavior from a single faulty input turned a supposed safety feature into a deadly hazard, creating an insurmountable challenge for the cockpit crew. Following the Lion Air crash, Boeing issued an operations manual bulletin reminding pilots of existing procedures for runaway stabilizer trim. Crucially, this bulletin did not explicitly mention MCAS or its role in the crash. It framed the issue as a procedural one, implying that pilots simply needed to follow established protocols. This approach suggested a downplaying of the severity of the MCAS flaw and its potential to overwhelm crews. Critics argue that this initial response lacked transparency and failed to adequately warn the global pilot community about the true nature of the risk inherent in the 737 MAX design. The FAA also issued an airworthiness directive, but it was based on Boeing's limited information. Tragically, just 5 months after Lion Air, on March 10, 2019, Ethiopian Airlines Flight 302 crashed shortly after takeoff from Addis Ababa, killing all 157 people on board. The world watched in disbelief as reports emerged of striking similarities to the Lion Air accident. Once again, a brand new 737 MAX 8 plummeted to the ground. This second catastrophe, occurring so soon after the first, eliminated any doubt that the problem was systemic and directly linked to the aircraft's design. It ignited global outrage and forced aviation authorities worldwide to take decisive, unprecedented action, shaking public confidence in Boeing to its core. Analysis of the Ethiopian Airlines black box data confirmed a chilling resemblance to the Lion Air flight. Both aircraft experienced faulty angle of attack sensor readings almost immediately after takeoff. In both cases, MCOS activated repeatedly, forcing the nose down, and the flight crews struggled desperately to counteract the system's commands. The flight profiles, characterized by oscillations in pitch and airspeed, were eerily parallel. This irrefutable evidence left no room for individual operator error or isolated mechanical failure. It squarely pointed to a fundamental design flaw within the 737 MAX flight control system, specifically MCOS. In the wake of the Ethiopian Airlines crash, global aviation authorities, one by one, began to ground the Boeing 737 MAX fleet. Initially, the FAA resisted, but facing immense international pressure and growing evidence, it eventually joined the global consensus. On March 13, 2019, the FAA issued an emergency order grounding all Boeing 737 MAX aircraft in U.S. airspace. This was an unprecedented move for a modern commercial aircraft, highlighting the gravity of the crisis. The grounding removed nearly 400 aircraft from service worldwide, sending shockwaves through the aviation industry and severely damaging Boeing's reputation. Delving deeper into MCOS, its aggressive nature was a critical flaw. Unlike typical flight control systems designed for subtle corrections, MCOS was programmed to make large, decisive nose-down inputs. These inputs, up to 2.5 degrees of stabilizer trim, were often beyond what a pilot could easily overcome with manual control, especially when battling repeated activations. The system's design essentially allowed a single, malfunctioning sensor to command a potentially catastrophic flight path, overriding pilot inputs without adequate warning or a simple, obvious way to disable it when things went wrong. This overreach made it incredibly difficult for even highly trained pilots to recover. A fundamental principle of aviation safety is redundancy, multiple systems or sensors to provide backup in case one fails. Yet, MCOS controversially lacked this. It relied solely on one of the two angle of attack sensors for its input. In modern aircraft, critical systems typically cross-check data from multiple sensors. Had MCOS compared both AOA sensors and only activated if they agreed, or at least alerted pilots to a discrepancy, these crashes might have been avoided. This omission represents a severe design oversight, an apparent compromise between engineering robustness and the desire to minimize complexity and additional costs in the certification process. Perhaps one of the most damning aspects was the minimal information provided to pilots about MCOS. Boeing deliberately downplayed the system's significance, removing any mention of it from pilot operating manuals and training materials, deeming it a background system that pilots wouldn't need to interact with. This meant pilots had no understanding of how to recognize, diagnose, or counteract MCOS if it malfunctioned. Simulator training, which would have exposed pilots to these scenarios, was deemed unnecessary by Boeing and accepted by the FAA, saving airlines millions but leaving pilots dangerously unprepared for an emergency of this nature. The Federal Aviation Administration, FAA, traditionally the global gold standard for aviation safety, came under intense scrutiny for its certification of the 737 MAX. Critics argued that the FAA's oversight was compromised by a combination of budget cuts, an outdated certification process, and an over-reliance on Boeing itself to perform safety assessments. This self-certification model, known as Organization Designation Authorization, ODA, allowed Boeing employees to act as representatives for the FAA, creating an inherent conflict of interest. The system meant the fox was, in effect, guarding the henhouse, leading to critical aspects of the MAX design receiving inadequate independent review. The Organization Designation Authorization (ODA) program was a cornerstone of the FAA's certification process for the 737 MAX. Under ODA, Boeing delegated significant responsibility to its own engineers to conduct tests and verify compliance with FAA regulations. While intended to streamline the certification process, critics argued that it blurred the lines between regulator and regulated. Boeing employees, under pressure to meet aggressive deadlines, were effectively signing off on their own company's work, creating a system ripe for potential oversights and conflicts of interest. The MAX crisis laid bare the inherent risks of this model, prompting calls for significant reform and increased independent oversight. Adding to the challenges, the FAA had faced decades of budget cuts, leading to significant understaffing in its certification division. From 2008 to 2018, the FAA's aircraft certification workforce reportedly decreased by over 10%. This reduction in personnel meant fewer FAA experts were available to directly scrutinize complex new designs, increasing reliance on the ODA program and Boeing's internal assessments. A smaller, less resourced regulatory body was ill-equipped to handle the pressures of certifying a rapidly developed, highly complex aircraft like the 737 MAX, especially when faced with an industry giant determined to meet tight market deadlines. Boeing's intense desire to get the 737 MAX to market quickly, often referred to internally as Gate 2 by analysts, was a significant factor influencing decision-making. The company aimed to beat Airbus's A320neo, which was already racking up orders. This pressure translated into an accelerated development timeline and an emphasis on minimizing changes to the existing 737 airframe to avoid costly and time-consuming new certifications. This speed-to-market mentality, while understandable from a business perspective, contributed to decisions that compromised safety margins, such as the classification of MCOS as a minor change, thus avoiding rigorous scrutiny. The decision to certify the 737 MAX as a derivative of the existing 737 rather than a new aircraft type proved to be a critical loophole. This allowed Boeing to avoid much stricter certification requirements, particularly for pilot training. MCOS itself was initially presented to the FAA as a minor change to the existing flight control system, further bypassing rigorous scrutiny. This classification meant less documentation, fewer test flights, and ultimately, a less transparent process. The regulatory framework, designed for incremental improvements, was not robust enough to catch the systemic risks introduced by significant, yet understated, software changes. Many inside and outside Boeing observed a profound cultural shift following the McDonnell-Douglas merger. The company, once led by engineers with deep aerospace expertise, increasingly saw MBAs and financial executives rise to the top. This change arguably shifted priorities from long-term engineering excellence and safety to short-term financial performance and shareholder returns. The focus became maximizing profits, boosting stock prices, and cutting costs, sometimes at the expense of meticulous design and rigorous safety testing. This evolution in leadership philosophy fundamentally altered how risk was perceived and managed within the company. The relentless drive for cost reduction permeated many aspects of Boeing's operations. This included reducing research and development investments, pushing suppliers for lower prices, and even outsourcing critical software development to lower-wage countries. For instance, reports indicated some 737 MAX software was developed by engineers earning as little as $9 an hour. While such measures could save money in the short term, they risked compromising quality and introduced complex supply chain challenges that could dilute oversight and control. This focus on immediate savings contributed to a culture where efficiency sometimes trumped fundamental safety concerns. Multiple reports surfaced detailing concerns from Boeing engineers about pressure to cut corners and certify systems quickly, especially for the 737 MAX. Whistleblowers and anonymous sources recounted instances where their safety concerns were downplayed, ignored, or overruled by management driven by aggressive schedules. This climate discouraged open communication about potential risks, fostering an environment where speaking up could be detrimental to one's career. When expertise is sidelined for expediency, the consequences can be dire, as tragically demonstrated by the MAX crashes. The internal checks and balances inherent in a strong engineering culture had eroded. Before the grounding, Boeing was aggressively ramping up 737 MAX production to meet burgeoning demand, reaching an unprecedented rate of 52 aircraft per month. Such high-volume production can put immense strain on quality control and manufacturing processes. Workers reported feeling rushed, leading to potential shortcuts or overlooked defects. While not directly linked to MCOS, a high-pressure production environment can indicate a broader cultural problem where speed and quantity are prioritized over meticulous attention to detail. This pressure contributed to a pervasive sense of urgency that, when combined with other factors, created fertile ground for errors to go unnoticed. Modern aircraft are essentially flying computers, with intricate software controlling nearly every aspect of flight. The 737 MAX crashes highlighted the critical need for meticulous testing and verification of these complex systems. Software, unlike mechanical components, can fail in unpredictable ways, especially when interacting with faulty sensor inputs or unexpected environmental conditions. The MCOS system, while seemingly a small addition, introduced a layer of software complexity that was not fully understood or adequately tested in all potential failure scenarios. This underscores the challenge of integrating new digital systems into legacy designs, where unforeseen interactions can have dire consequences. After the global grounding, Boeing embarked on an urgent and comprehensive effort to overhaul the 737 MAX flight control software. This involved significant modifications to MCOS, aiming to address the flaws that led to the crashes. The process was lengthy, requiring extensive testing, simulation, and review by global aviation authorities. The goal was not just to fix the immediate problem but to regain trust. Engineers worked tirelessly to reprogram the system, implementing safeguards that should have been in place from the outset, demonstrating the immense technical challenge of retrofitting safety into a system that was fundamentally flawed in its original design. The core of the software fix addressed the lack of redundancy. The updated MCOS now takes input from both angle of attack sensors. If the sensors disagree by more than 5.5 degrees, MCOS is disabled, and an alert is triggered in the cockpit, providing pilots with crucial information. Furthermore, the updated system only activates once per event, preventing the aggressive, repeated nose-down commands that overwhelmed the crews in the crashes. Its authority to pitch the nose down is also significantly limited. These changes represent a fundamental redesign of MCOS, prioritizing safety by building in multiple layers of protection and pilot awareness. Another critical component of the recertification was the overhaul of pilot training protocols. Gone were the days of iPad-based modules. Regulators worldwide mandated comprehensive simulator training for all 737 MAX pilots. This training specifically includes scenarios where MCOS malfunctions, ensuring pilots are fully aware of the system, can recognize its errant behavior, and know how to effectively disable it and regain manual control. This represents a significant shift, acknowledging that MCOS was not a minor background system but a critical flight control element that required thorough pilot understanding and proficiency to manage safely. It was a concession Boeing had initially resisted. The path to recertification was long and arduous, spanning over 20 months. It involved extensive flight testing by the FAA, European Union Aviation Safety Agency, EASA, and other global regulators, independent reviews of Boeing's software fixes, and public hearings. The process was under intense scrutiny from grieving families, politicians, and the public. Each regulator conducted its own independent assessments, often demanding additional safeguards beyond the initial FAA requirements. This global effort, though challenging, ultimately aimed to restore confidence in the aircraft and the regulatory system, ensuring no stone was left unturned in verifying its safety. The 737 MAX crisis inflicted a staggering financial blow on Boeing. The grounding cost the company an estimated $20 billion in direct costs, including compensation to airlines for grounded planes, production halts, and legal fees. Beyond that, countless billions were lost in cancelled orders, reduced stock value, and a damaged brand. The crisis forced Boeing to dramatically cut production, leading to significant layoffs and disruptions across its supply chain. This financial devastation underscored the immense economic consequences when safety is compromised, illustrating that shortcuts often prove far more costly in the long run than proper investment in engineering and quality. More damaging than financial losses was the severe blow to Boeing's century-old reputation for safety and engineering excellence. A brand once revered for its meticulous attention to detail and unwavering reliability was now associated with catastrophic failures. Public trust plummeted, with many passengers expressing apprehension about flying on a 737 MAX. Rebuilding this trust will be an ongoing, multi-year challenge. The crisis served as a stark reminder that a company's most valuable asset is its reputation, built on consistent performance and a commitment to core values. Once shattered, it is incredibly difficult to mend, impacting sales and stakeholder confidence for years. The crisis prompted significant leadership changes at Boeing. CEO Dennis Muilenburg was ousted in late 2019, replaced by David Calhoun. Other senior executives involved in the 737 MAX program also departed. This represented an attempt by the company's board to signal accountability and a fresh start. While leadership changes are often symbolic, they are crucial for restoring investor and public confidence. The new leadership faces the daunting task of re-establishing an engineering-first culture, prioritizing safety over financial metrics, and rebuilding the company's relationships with regulators and customers. The challenge is immense, requiring sustained commitment and transparency. The 737 MAX crashes triggered widespread calls for significant reforms to the FAA's aircraft certification process and its relationship with manufacturers. Lawmakers and international bodies demanded greater independence for the FAA, reduced reliance on the ODA program, and increased transparency. There was a consensus that regulatory agencies needed more resources and a stronger mandate to conduct independent oversight, free from industry pressure. The crisis provided a painful but necessary impetus to re-evaluate how aircraft are certified, ensuring that safety is always the paramount consideration, not just a box to be checked, fostering a more robust global safety net. Throughout the crisis, whistleblowers played a crucial role, bringing to light internal concerns and pressures that contributed to the MAX flaws. Employees, often at great personal risk, provided invaluable insights into a corporate culture where cost and schedule sometimes trump safety. Their testimonies revealed a pattern of internal warnings being ignored, design shortcuts being approved, and an environment where dissent was stifled. These voices underscored that systemic problems are often known internally long before they manifest in tragic ways, highlighting the critical importance of protecting and empowering those who speak up for safety. The decision to outsource critical software development for the 737 MAX, particularly to contractors in lower-wage countries, raised significant quality control concerns. While cost-effective, such arrangements can complicate oversight, communication, and the consistent application of safety standards. Reports suggested some software code was written by developers with limited aviation experience, working under tight deadlines. This fragmentation of development, combined with a lax internal review process, created vulnerabilities. It highlights how a focus on cost-saving and development can lead to unforeseen complexities and risks in critical systems, emphasizing that not all tasks are equally suitable for outsourcing, especially in aerospace. Boeing's intense pressure to cut costs and accelerate production extended to its vast network of suppliers. These companies were often pushed to meet aggressive delivery schedules and provide components at reduced prices. This relentless pressure, while good for Boeing's bottom line, could lead to quality compromises throughout the supply chain. When suppliers are struggling to meet cost and schedule demands, the focus on meticulous quality assurance can inadvertently suffer. This created a ripple effect, potentially introducing weaknesses into various aircraft components and systems, even if indirectly related to the MCOS issue itself, reflecting a systemic issue in the broader production ecosystem. At the heart of both tragedies were the flight crews who, despite their training and experience, were overwhelmed by an automated system they did not understand. The Lion Air and Ethiopian Airlines pilots fought valiantly against repeated, erroneous commands, but they were in an unwinnable battle against a system designed without adequate safeguards or pilot awareness. The crisis underscored the critical importance of the human factor in complex automation. Systems must be intuitive, transparent, and allow for clear human intervention. When automation fails catastrophically, pilots must be equipped to take full control, not rendered powerless by unexpected software behavior. Investigations and whistleblower accounts revealed a culture of yes at Boeing, where managers and engineers felt pressured to agree to aggressive timelines and cost targets, even when expressing reservations about safety or design. This environment discouraged dissenting opinions and rewarded compliance, fostering a climate where critical concerns might not be escalated or adequately addressed. When the drive for commercial success overshadows open communication and critical self-assessment, the foundational principles of engineering integrity are compromised. This internal pressure to conform ultimately contributed to the systemic failures that led to the MAX crashes. In the years since the grounding, Boeing has embarked on a long journey to rebuild its reputation and safety culture. The company has publicly committed to prioritizing safety, strengthening its engineering voice, and improving transparency with regulators and customers. This involves significant internal reforms, enhanced training programs, and a re-evaluation of its certification processes. While progress is being made, the path to fully restoring trust is extensive. The company is under constant scrutiny, every new aircraft delivery and safety incident now examined through the lens of the MAX crisis, demonstrating the lasting impact and the imperative for genuine, sustained change. Despite the recertification, the market reaction to the 737 MAX remains cautious. Airlines have canceled hundreds of orders, delaying deliveries and opting for competitor aircraft. While some carriers have successfully integrated the MAX back into their fleets, others remain hesitant. This reluctance reflects not just the operational challenges of the grounding but also lingering concerns about the aircraft's public image and the company's reliability. The market's enduring skepticism underscores the depth of the damage inflicted by the crisis, showing that even with fixes, the shadow of past events can influence purchasing decisions for years, impacting Boeing's market share and future aircraft development. For passengers, the return of the 737 MAX has been met with a mix of acceptance and continued trepidation. Airlines and Boeing have launched campaigns to reassure the public about the aircraft's safety, emphasizing the extensive software updates and enhanced pilot training. Yet, some travelers actively seek to avoid the MAX, checking aircraft types before booking flights. Restoring deep-seated public trust is a slow process, built on years of incident-free operation and transparent communication. It will require Boeing to consistently demonstrate its renewed commitment to safety, proving through actions, not just words, that the lessons of the past have been fully learned and integrated. The MAX crisis sparked a critical debate about the delicate balance between automation and human pilot control in modern cockpits. While automation enhances efficiency and can improve safety by reducing human error, it must never overshadow a pilot's ability to understand, override, and control the aircraft, especially in abnormal situations. The crashes highlighted the dangers of automation surprise, when systems behave in ways pilots don't expect or aren't trained for. Moving forward, the industry must ensure that pilots remain in command, fully informed and capable of intervening, with automation serving as a helpful tool, not an inscrutable master. This balance is crucial for future aircraft design. The 737 MAX crisis served as a profound and painful lesson for the entire aerospace industry. It underscored the absolute necessity of robust design principles, independent regulatory oversight, and an unshakable corporate culture of safety. The takeaways are clear: critical systems must incorporate multiple layers of redundancy, pilot training must be thorough and transparent, and regulators must have the resources and independence to rigorously scrutinize every aspect of aircraft certification. These aren't just suggestions, they are fundamental tenets that must be upheld to prevent future tragedies and maintain the highest standards of aviation safety globally. So, what was the real reason Boeing's new plane crashed twice? It wasn't a single isolated factor, but a complex, tragic convergence. A design flaw in MCAS, driven by the need to adapt an old airframe with new engines. A regulatory failure by the FAA, stemming from budget cuts and a reliance on self-certification. And, perhaps most profoundly, a cultural shift at Boeing, where financial pressures and speed to market seemingly overshadowed its historic dedication to engineering excellence and safety. These interconnected failures created a domino effect, leading to 2 catastrophic crashes and a global crisis that changed aviation forever. It was a failure of the system, not just a system failure. The shadows of Lion Air and Ethiopian Airlines will forever hang over the 737 MAX, a stark reminder of the devastating consequences when safety is deprioritized. While the aircraft has returned to service with critical software updates and enhanced training, the imperative for constant vigilance remains. For Boeing, for regulators, and for the entire aviation industry, the lesson is clear: true innovation must always be tempered by an unwavering commitment to safety. The lives lost serve as a solemn pledge that such a complex, preventable tragedy must never be allowed to happen again, demanding continuous improvement and an enduring dedication to the highest standards of airworthiness.